So this relativistic covariance of Dirac equation demands that Dirac field or this wave function should transforms in this way, where S is a 4x4 matrix which satisfies this relation. Okay, this was discussed in the class and it was also written in the class notes. You just go through it. Now we wanted a form of this function S, this transformation matrix, 4x4 transformation matrix. To obtain that form, we first argued that since Lagrange transformations form a group, therefore, if we can find the S sigma, S lambda for an infinitesimal transformation, from that infinitesimal transformation, operating successive many infinitesimal transformation, we can generate a finite Lagrange transformation, because successive operations of Lagrange transformation will also lead to a Lagrange transformation because it is a group. Okay, so it is easy for us to find out the form of this transformation matrix when this argument lambda, which is the basically the Lagrange transformation matrix, when this represents an infinitesimal transformation. In that case, we find the value of this form of this S. Okay, so for an infinitesimal Lagrange transformation, I can write it this way, and this is antisymmetric. Okay, now when you can write it in this way, so the parameters of the transformation are inside this W or omega. Okay, and you see that because of this antisymmetry, out of the 16 possible components, only 6 are independent. Okay, which I can choose to be this 6. Okay, so the diagonals are 0. So omega 0, 0, omega 1, 1, omega 1, 2, omega 3, 3, they are all 0. And there are 12 other off diagonal elements, 6 of which are negative of other 6. So I have chosen the 6 independent parameters as this. So omega 1, 0 will be omega minus 0, 1, like that. Okay, so there are 6 parameters which describes this infinitesimal Lagrange transformation, and because of the now we want to know what will be the form of the S omega. Okay, so sorry, S lambda, where S satisfies this relation. So this was the setup. So S lambda must be a linear function of these Lagrange parameters, obviously, because whatever form it has, it must be a linear in omega, because omega square being infinitesimal, omega square and omega cube and other higher order terms can be dropped with respect to the linear term, because it is infinitesimal or less than this. Okay, therefore I can straightforward write S of this as 1 plus a linear combination of all this without any linear dependence on all these omegas, without any square term or cubic term. Okay, there is also no omega 01 into omega 02 term because it is linear. This I comes because of this fact that when all these omegas are 0, this matrix is just the identity, or in this form it is the Minkowskian metric. Therefore, when all the omegas are 0, then this must be identity, because Dirac field then doesn't transform. Okay, and this should be identity. When omega lambda is 0, when omegas are 0, then lambda is 1, identity matrix, and S lambda should also be identity. Sorry, lambda is not identity. When omegas are 0, S lambda must be an identity matrix, so that no Lagrange transformation means omega equal to 0, and therefore psi prime x prime is and psi x are identical. Okay, therefore this I is there, sitting there, and this part, which is the non-identity part, or which is the contribution from the infinitesimal Lagrange transformation, must be linear in these parameters, because we have taken infinitesimal Lagrange transformation. Clear? where since this, remember these are all single parameters. Okay, 6 independent parameters which has a single valued parameters. Therefore, but since S omega is a 4 cross 4 matrix, S lambda is a 4 cross 4 matrix. So I should be a 4 cross 4, but these things which are looking like coefficients, these are also 4 cross 4 matrix. So that this is a matrix equation. Clear? So all these A's are here, A1 to 6 are 4 cross 4 matrices. And therefore, and they should be constant. In this constant means here they are not dependent on space-time or neither omegas. Okay, they are just some numerical numbers, real or complex, but these are constant matrices which shows the dependence of omegas on S. Okay, now this expression can simply be written in this way. Okay, because you see omegas are I have stated the reason, because all the omegas are antisymmetric with respect to its indices. Therefore, look at this expression. So all nu mu runs from 0, 1, 2, 3. Okay, so since omega nu mu is antisymmetric, omega 0, 0, omega 1, 1, they are anyway 0, and omega. So in this expression, there are 16 terms, 4 of which are 0, and other 6 are negative of this 6. To ensure that, I introduced this matrix beta mu nu. And if we say that beta mu nu is also antisymmetric with respect to mu nu, then this beta mu nu corresponds to a set of 6 matrices, 6 independent matrices like this. Okay, or to be clear, in other words, we just write this A1 matrix, A2 matrix, A3 matrix in this way in terms of this beta. Okay, so there are 6. Yes.
In the first line, beta mu nu equals to minus beta nu mu, it is covariant should be.
Yeah, this is
contravariant.
Yeah, sure. This is the mistake. Right. These are obvious mistakes, you know, you can just correct it. Okay, thank you. So, but if you can write beta mu nu down and omega mu nu up, that will not change things. Okay, so suppose you, okay, I should have written beta 0, 1 in the above here. Okay, I will correct it. Okay, thank you. But the point is, if you write all these A's, 6 A's in terms of by a symbol where these 1 to 6 are just written in by this combination of indices like 0, 1, 0, 2, 0, 3, 1, 2, 2, 3, 3, 1, then using this repeated index symbol, I can simply write this in a shorthand notation like this, where you ensure that beta mu nu represents a set of matrices where such that this set of matrices represented by beta mu nu are antisymmetric with respect to mu nu. Therefore, effectively there are 6 matrices. Clear? But to it is easier to work with this simpler form, rather the same form, but it is a simple looking form. Okay, because of this introduction of beta mu nu. Now, if S sigma is this, you can obviously check inverse of this matrix. S lambda is this, inverse of this matrix should be this. Why? Because their product should give you identity if you multiply it. So this multiply by this, it will give this 1, and this cross term will cancel because of this plus and minus sign, and there will be a term where this is multiplied by this. When you multiply this by this, you have to change these indices to a different thing. So alpha, beta, alpha, like that. But all the terms of this product should carries second order terms in omega, because there are 2 omegas. Therefore, that can be dropped with respect to the identity. So for infinitesimal transformation, you are left with, if this represents this transformation matrix, its inverse will be this. And we know that in this matrix should satisfy this relation. If this represents the Lorentz transformation matrix for the Dirac field, then this relation has to be satisfied. Now you put these forms of S omega and S inverse omega in this, okay? And if you put here in this, then this is an exercise. You can check that this matrix beta should satisfy this relation. I have not done it because maybe you have done it in class, or if you have not done, you have to do it yourselves. Okay, but this is a very good exercise to warm up with the algebra of gamma matrices. Clear? If you do so, then this matrix beta, which appears where? Which appears here in the, form of the infinitesimal Lorentz transformation matrix. That matrix, you get some information that matrix should be such that this condition should be satisfied, or in other words, this condition should be satisfied. It is just a translation of this equation to this in terms of this matrix. Okay, where gamma matrices are known matrix in the sense that you know that they satisfy Clifford algebra, and etas are just these what is that, Minkowskian metric. Okay, so the question is whether we can find such a matrix beta which satisfies this commutation relation. Okay, now again I directly give you the answer. If you choose beta mu nu as the commutator of gamma mu and gamma nu, okay, this is not anti-commutator. Anti-commutator, if anti-commutator is equal to eta mu nu, but if you choose the commutator of this, which becomes which is also a matrix, but a matrix which must be referred by these two indices. Mu nu. Beta mu nu itself is a matrix. For every mu nu, beta mu nu is a matrix. Okay. So if you write it in terms of the known gamma matrices, which are known because you know that they satisfy Clifford algebra, then you can check that this condition is satisfied for this form of matrices. Now, any of you in a position to say that you have verified this, or directly from here you can see this form of beta mu nu? Have you done this, or in your class or in your exercise, or that?
Yes, in the class we have done this.
Okay, that is very good. Okay, so this is so for infinitesimal Lorentz transformation, at least we can say summary that for an infinitesimal Lorentz transformation, this transformation matrix should be of this form where this quantity is this commutator. Okay, we will later see that this represents this is the matrix representation of the spin operator. Okay, we will see slowly. But so far as Lorentz transformation is concerned, this is the general form of the Lorentz transformation for when the transformation is infinitesimal. So when you want to work with when you deal with a problem, in some cases you need to use the explicit form of this matrix. Then you have to use this for infinitesimal Lorentz transformation. For finite Lorentz transformation, it will just be successive products of this. Okay, there is no point of studying a finite Lorentz transformation, because you know that many such successive transformations of this will give you the finite Lorentz transformation. So if you multiply it by, if you raise it to the power n by and divide the total omega nu mu by n, what it will be? So if you have finite Laurentz transformation, you break it by n parts and then do the successive transformations. So this will look like exponential of this thing. Okay. So I will not go into that. I will come to this later. But for the timing, it is enough to understand, for our purpose, it is enough to understand that for an infinitesimal transformation, the Dirac transformation matrix for the Dirac field looks like this. And if you want to do with what is going on with finite transformation, then instead of using that, you can just directly use this relation, where this is for any general finite transformation, where S should satisfy this relation. Clear? And you can use, sorry, and you can use the form of this equation, this property of S, without you don't, in many cases you don't need to put any form of S. You can use just this equation, S satisfying this equation, to investigate further the properties of the Dirac field. We will see that. Okay, but this bottom line is we now know how a Dirac field transforms under Laurentz transformation. Okay, the transformation matrix we know, for at least for an infinitesimal transformation. For a finite transformation, I know what equation S lambda has to satisfy. Clear? So this was the material of the last class. So let's begin today's content. So we will, I spoke to Sanjay. He will teach this part also in his course, but I will teach this parts. I will teach these topics because I will need the results from this topic. So I will teach very briefly. He will teach elaborately. Okay. Now, first look at that. Now you have Dirac equations. Klein-Gordon equations. Dirac equation is the relativistic wave equation for a system particle. Klein-Gordon equation is also a relativistic wave equation of a particle. True that Klein-Gordon equation doesn't have any proper interpretation for probability density, but Dirac equation has. Okay, but whether Klein-Gordon or Dirac equation, they are the relativistic wave equations. Okay. Now, when you study classical mechanics, the equation of motion of the system is this. Clear? This is the equation of motion of a system, and you put, if you use action principle, this is directly derivable from the action principle theoretically. Clear? So if you know the form of the Lagrangian and put it here, then you get the equation of motion. Okay, like if you know the Lagrangian for a central force particle moving in a central force field, you put this Lagrangian here, the equation, you will get this equation will give you the equation of motion for that particle in a central force field. Yeah? So equation of motion describes the dynamics of a system. But in classical mechanics, if you want to know the dynamics of the system, so what is the equation of motion? Equation of motion is basically a connection. So you know that equation of motion in classical mechanics is basically a connection between the acceleration, the velocity, and the coordinate. Okay. So this equation connects these three quantities. If there are more degrees of freedom in the system, so Q1 double dot, Q2 double dot, Q3 double dot, etc., all are connected to this their lower derivatives. So acceleration gets connected to velocity and position, and you say that this is the equation of motion of the system. And this is every system has its own equation of motion. Okay, that is natural. Now, in classical mechanics, when you, just a minute, I am taking, so I have to drink water for just. But when you start formulating the Lagrangian dynamics, Lagrangian formulation of classical mechanics, then at the very beginning, you assume that the configuration of the system is described by some generalized coordinates, which are functions of time. The configuration and the state of motion of the system together are described by the coordinates and the velocities. Okay, so if you want to know, so the dynamics of the system is described in terms of this two quantities. You don't need q double dot because q double dot is automatically related to q dot and q. And because you believe at the very beginning, you assume that there must exist a relation between these two, or in other words, equation of motion for the system exists. Clear? So you all studied this in classical mechanics class. Now, suppose a system is described by a Klein-Gordon field or a Dirac field. So what kind of system is this? This must be a subatomic particle or microscopic system which is relativistic. Such a system is described by a field, a wave function. Yeah, a wave function which satisfies a relativistic wave equation, not Schrodinger equation. Okay. Suppose a system is described by a field. Okay, this field is called a classical field because this field is a number, classical number. It may be a complex number, it may be a real function, complex function, but it is a number. So it may be Dirac field, sorry, Klein-Gordon field, it may be Dirac field. In principle, it may be the electromagnetic field E and B, or this mu, which is the electromagnetic vector potential. Okay. So this is a classical field. Okay. So this field, now the whole system which is described by the field at any point of time t, just a minute, at any point of time t, the complete description of the configuration of the system means knowledge of this field. Like this field serves the role of generalized coordinate for the system. That means if you know this value of the field, okay, for at any time, if you know this value for all values of x, okay, then you say that you know about the configuration of the field. That is you know about the system at every point at any instant of time. You know the value of that function at every point in space. Okay. Now there may not be any single function. There may be 2 or 3 or more functions associated with the description of the field. So I put the index R, which means R can be any finite number, 1, 2, 3, 4, 5. So that there are 5 fields which represents the system. For example, if you try to understand this very carefully, if you want to describe light, okay, light suppose in your room there is light, you have switched on your light. So at every point in space, you see an intensity of light. Now, if you think light to be a wave, not as a particle like photon, it comes later. If you think light, you want to describe light as a wave. That means light is an electromagnetic wave. That means at every point in space-time, there is an electric field, okay, and a magnetic field. And these are vector quantities. That means all these are vector quantities. So that means to describe the electromagnetic field in your room, what you have in uh, uh, assuming light to be an earth, to describe the electromagnetic field in your room, what you can say that I know the complete, I know about everything about this electromagnetic field in my room. That means you know what is the value of this field at every point in space of your room at all instants of time. Okay, so that means you need basically how many numbers you need to describe, how many numbers you need to describe the electromagnetic field at your room at a particular time. Can you tell me?
Uh, Two independent component we need, because other components are fixed by gauge invariance.
Forget about gauge invariance. Suppose at every point of time, you want to, you
Fixed
don't look for,
components.
at every point in, sorry, at any instant of time, you want a complete description of the electromagnetic field in your room. So at that point, only at one point of time, say at 10 p.m., you want to know what is the situation, that what is the nature of electromagnetic field in my room. I want the complete description. For that, how many numbers you need?
4 numbers.
Okay, why 4?
If we know the potential, we can find the entire E vector.
No, no, no. Okay,
And
okay. So you are saying that this, okay, this phi and a. Are you saying this?
yes, yes, right.
Okay, in that. Okay, so let's talk in terms of phi and a. Let's talk this in these terms. Just a minute. Phi is a function of what? X and t. It is the scalar potential and the vector potential, which is also a function of x and t. And if you know phi and a, you can directly calculate from this phi and a the value of electric field and magnetic field. Okay, but here you have this just 4 degrees of freedom, 3 components of this, and one phi. Okay, so if you know this, as you are saying, if I know these 4 numbers at any point of time, then I know the description of the field. But there is a subtlety here. These are not 4 numbers. This is a function. Clear? So if you want to know exactly what is this, what is the field configuration, electromagnetic field configuration in your room at any particular point, fixed point in time, at a particular point in time, say at now 3:37 p.m. Okay, then total number you required is infinity, because at this point of time you have to specify the values of phi a at all points of x,
Oh, yes, yes,
at
right.
all space time
Yes.
points. So this is a system with infinite degrees of freedom. If, do you understand? I want to specify suppose an electromagnetic field. In this case, a field has a property at every point in space time, it has a value. Now I want to know, I gave a status time t as a parameter. With respect to this parameter, I see the change in field configuration, like I do for classical mechanics. For a fixed t, I look at the different coordinates of the system, how the coordinate changes. But now, what happens? Both these fields, both these functions are functions of time. That means if you want to know the value of this t, sorry, the field configuration in any place, you have to know the numerical value of this field at every point in space, phi and a at every point in space. Okay. So at this point, next point, at next point, at next point, and next point, and next point, you can say this, that is contained in the form of the function, but we are not taking the form of the function. What we are trying to do, a system of field, a system described by a field. I want to map it, or I want to see it. I want to do a Lagrangian formulation of it, so that for that purpose, I want to first fix what are the generalized coordinates of the system. Now, generalized coordinates by definition means the number of independent parameters you require to specify the system at any given time. Okay. Now, at any given time, the number of parameters required to specify the electromagnetic field in your room are not 4, they are infinity. Is it clear? Just as far as the number of parameters are concerned, number of quantities which you need to specify your field configuration in your room is infinity, because there are infinite points in space, infinite spatial points in your room, and at every point there is a value. So, is it clear?
Sir, if we fix our spatial point, then we have
you can't fix your spatial point. That is the point, because your system is a field.
Okay.
The phenomena, suppose an electron, okay, suppose a particle, suppose an electron, which is relativistic. It is described, if you combine special relativity and quantum mechanics in a way we have done so far, it should be described by a wave function psi, which satisfies Dirac equation. Okay, that's psi is dependent on xt. Clear? Now you want to specify, now what is this? Your system is a relativistic electron. Now if you want to specify the state of the system completely in terms of, by specifying the configuration of the system, what you have to do, you have to specify the value of psi at every point in x. If you specify psi at one point in the x for a given x at any time, you need you need one such matrix. I mean, just 4 numbers, because there are 4 components of this. Okay. But that is the description at a particular point in space. Okay. So when you study classical mechanics, time is your time is your parameter with respect to which you determine your all other quantities in your theory are just functions of this independent quantity time. Okay. Now here, this entire field describes your system. That means at any particular time, all the values of the function, you need the entire functional form to describe the system, which means you need values of the function at all points of x for that time. Okay. Now, if we want to map this, if we want to look into this in a way just as a classical system described by its degrees of freedom, described by its generalized coordinate, then what we have to do, this quantity, which is the corresponding classical quantity, the qi, where this I stands for a particular degrees of freedom, qi, the generalized coordinate corresponding to that degree of freedom as a function of time, that quantity is like this, where x, t is the parameter here, t is the parameter also here, but here we can think that x, as if x has the status of this index I, because at any point of time you need, forget about this r, you need the value of this field at x point, at the second point, at the third point in space. So all together tells you what is the field at in your entire space. That is the complete description of the system. In that sense, the position is treated as a parameter, but equivalent to the index I here. Is it clear? Is it clear? To describe the configuration of a
Why
field.
parameter?
Yeah?
Why parameter you said? Oh,
See, you want to know how the field in your room changes. In this question, there is no reference to the position. You just, there is a room, and in your room, there are infinite spatial points. You want to know, or in universe, say, the whole, your room is the universe, how the field in this universe changes. Now, how this changes means, you suppose, now, if you fix time, okay, if you fix time, if you look at a particular time, different points of your universe will have different values of the field. At different spatial points, you will have different values at a particular time. Is it clear? At a particular time, at different points in space, the field will take different values. Clear?
yes, yes.
Then, now you want to, how you will describe the field configuration of the system at that point. You have to specify all these values. You have to specify all these values for that particular time. You have to specify what is the value, numerical value of that field at this point, at the next point, at the next spatial point, and they are continuous points. Okay. So this, so you are, in other words, if you can write that, if you, so this field psi at x1, okay, at psi, the same field psi, the value of the field at x2, okay, dot 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 up to at all x points. This forms the, these are the set of numbers at a particular time. Since at a particular time I don't write time as in the argument, at a particular time, all these numerical values completely describe the configuration of the field in your in the universe. In that sense, this set represents the generalized coordinate for the system, and there are infinite such generalized coordinates. You can ask if there is any doubt.
So, sir, here we put the values of x for a particular time t to get the complete.
No. For a particular time t, so you have a function, okay? So for a particular time t, you have a for a particular time t, it is true that for a particular time t, the whole field configuration of your space is described by this mathematical function or this mathematical function. For a particular t, if you know the form of dependence on x, you know the how at different points the field changes, and that is the description of the field. Okay, but if you want to formulate it in terms of generalized coordinate, the different values of this function at different points should serve are the role of generalized coordinate for this system. Because all of them together, this function as a whole, but this function of x as a whole describes the entire system. That means values of this function at every x, all are independent values. To begin with, you don't know, when you formulate classical mechanics, you take this q1, q2, q3 as generalized coordinates, and you assume them to be independent. Yeah. Then you don't know at later time, because at later time, all these values will take some different values. Then your field configuration changes. If I put it, if I want to visualize the evolution of a field configuration in the same way that a system which is described by a wave function or a field which has a particular value at any particular space-time point, that means field description means knowing the value of the field at all points at a particular time. Therefore, that those values of that field at all points, those quantities behaves as if like a generalized coordinates for the system, and which I write. Therefore, I can, so this is not a conventional way, but I write it here in this way because you take like you take different I, it becomes a different coordinate. Like here, you take a different x, it represents a different generalized coordinate. So values of different points, values of the field at different points are the different generalized coordinates values. They describe this field. Is this
Yeah, got it.
Can we say that a system is
can you be a little louder?
hello?
Huh.
Can we say that our system is like an ensemble with infinite number of microstates?
But then you have to define microstates. And
Microstates means
but
every
also macrostates.
field
Since you are
value.
since you are using the word ensemble, then you have to
Yes.
also refer to it the macrostates, because all the microstates have different microstates. All the different microstates should have same macrostate. That's an ensemble.
Yes.
It is like an ensemble. I mean, it is the. I mean, it is. So that, I mean, that macrostate microstate doesn't seem very good analogy for this. Best analogy is this thing. Just look at a classical system which is described by its generalized coordinates and momenta. Now, generalized coordinates only describe the shape of the system, which we say configuration of the system. Okay, so for a system with say 3 degrees or 4 degrees of freedom or n degrees of freedom, there are n generalized coordinates. That means to know what is the configuration of the classical system, you need n numbers, independent numbers. And to study the dynamics, you have to just see how this n number changes with time. Now, when a system is described by a field, say psi, but say for a single field psi, then to know the phrase, that configuration of the system, here system means the system of field. The system means a single relativistic electron, but its description needs infinite numbers. At a particular time, you can't say 1 or 2, though it is an electron, single electron, you can't just say it has 3 degrees of freedom. It has infinite degrees of freedom because it is represented by a relativistic field, and all the values of the field at all points should be taken into account to describe this electron. Clear? Therefore, this generalized coordinate, you think that this field psi in general field plays the role of generalized coordinate, but where x, this is not a single number. So think x thinks this x like this I. I takes different values. So there are infinite number of, so x takes different values. For every value of x, this quantity, for each value of x, this is a generalized coordinate. So there are infinite generalized coordinates. So here you just think that x is a variable. Like here, think I as a variable running from 1 to s, but think x is a variable running from 1 to infinity, but in a continuous way. X is a continuous variable. It's a slightly different. So x is continuous. Okay. And this R is a discrete index here. I just put for a general case, if a system like for electromagnetic field, you see there are phi and A. There are 3 vectors. So this R is 4 here. So you need 4 fields, but 4 types of value coordinates, but each of these fields take a particular value at a particular point. At different points, they take different values. So all at a given time, all the different values of these four fields at all points, the entire set. Okay. So at a given time, all the values of this field at all points, which is infinity, which is an infinite in number. All this set of infinite numbers you have to utter, or you have to specify to describe the configuration of the system at that time. It is not just phone numbers. I am talking not in terms of functions. I have to see in terms of numbers, because I want to describe the generalized coordinates of the system. I want to extract, put it in a form where I can use our methodology of formulating Lagrangian mechanics in terms of generalized coordinates. So I have to search what quantities behave as generalized coordinates for fields. And that is the value of the field at all space-time points. So there are infinite such values. All values are values of the generalized coordinates. All possible, they are all the different generalized coordinates. So this is the best way to represent that. So this is the generalized coordinates for the field. R can be 4 for electromagnetic field, and X can be anything, any point in space. So how many are there? These possible indices R and X are maybe 4, finite, but X should be infinite. So all this infinite set of quantities seen as a function of time behaves as a generalized coordinate for the system. Clear? Think of this. Therefore, so number of degrees of freedom of the system is infinity. Now, since to represent dynamics of a system, what do you need? Dynamics of a system is described in terms of the generalized coordinates and the generalized velocities, time dependence of these quantities. So for here also we need these quantities to represent the configuration and also the time derivative of this, because these are generalized coordinates, these are generalized velocities. Okay. Now there is another point. Another point is that X is a continuous variable here. X is a continuous parameter. Okay. X is a continuous parameter means as X changes, so as you go from one to other, as you move your focus from one generalized coordinate to other generalized coordinate, it should obviously be a different coordinate. Okay, but how much different these differences are as you change X, that depends on how the function depends on X. Clear? Is it clear? Therefore, for a proper description of the dynamics of the system, it should also depend on the space derivative of the function. When you generalize classical mechanical system to a system which is represented by a system of field, which is for a relativistic quantum mechanical system, which is described as a system of field. For that field of system, first thing is that you can choose your coordinates in that way, generalized velocities in that way. Also, there is a factor that because this X is a continuum, X changes continuously, the way these generalized coordinates change with X, you have also to take care. Is it clear? The system, the field which describes the dynamics of the system, the dynamics of the system is inherent in this, not only in the form of the field, but also in the time derivative of the field and also in the spatial derivative of the field, because space is a continuous parameter. Okay, so when you go from one generalized coordinate to, hello?
Sir, when we are doing classical mechanics, there the
Yes,
generalized coordinates is qi as a function of time.
yes,
So q1,
there,
q2, q3, they are generalized coordinates. Okay.
yes,
But when we are obtaining the equation of motion, there we don't don't do anything with the I index. Actually, we don't do anything like sum over index or anything mathematical something. But why
yes.
here we are?
Yeah, we are not doing
But
any,
here,
we are not doing any sum over x. We are not, so
yeah,
we are not doing, here also we are not doing sum over x, but here the fact that when you move from a discrete system to a continuous system, okay, then your this coordinate has a, like say, okay, look at it this way. Suppose you have two different field configurations. Okay, what does that mean? What does that mean? Two different field configuration means there are, you are talking about two different configurations. Say one is f of xt is one field. Okay, g of xt is another field. Okay, now when you consider fields, you took the generalized coordinates as f of x t, here g of xt. Clear? This is what I said just. So at all, so this is not a single number. This is not a single function of time. This is a set of infinite functions of time, each for different x. This is also so. This is also a set of infinite functions of time for each x. Okay. So these two are the two sets of generalized coordinates for the two different systems. Now, f has its own way of x dependence in this function. G has its own way of independence, x dependence in that function. That was not so in classical mechanics. I was a discrete number. I was not a continuous number.
yes.
Hello?
Hello, yes, sir.
Okay. So therefore, the dynamics of the system, which means how this function changes with time. Okay, how this set of functions changes with time. Here also how this set of function changes with time. Okay, so but only time dependence, there is time dependence here, but only time dependence will tells you how it changes with time, but the x dependence in the function, that x dependence is also decide, I mean, what should I say, that how this just a minute.
This in classical mechanics, this I changes running in discrete manner. So we know how q1, q2, how q changes under q1, q2,
Yes.
q3, etc. But in that case, how the function changes under the change of the x, actually the change, I mean how the
See.
function f.
So when you look, when you do classical mechanics, when you look, focus on a system, you first identify the generalized coordinates of the system. Okay, and these generalized coordinates, so you can't visualize this change from. So you go from Q1, you just this, if you just see these two relations between these two coordinate systems, these two generalized coordinates, they are just two independent coordinates associated with the configuration of the field, configuration of the system. Like if it is a like if it is a central force problem, these are, one is theta, one is phi. Theta and phi are two say two angles which have different geometric interpretations in your visualization. Clear? So if you want to see the difference between theta and phi, or any two generalized coordinates, so how that difference arises? That difference is there in the configuration of the system. It is not arising, but you are, when you are considering field, that is a generalization, and then this difference, one going from say this to another x, its next x. Okay, going from this to another x.
It is x to x plus dx, let's say.
Yeah. Let's say x to x plus dx. That thing, that change, you can suppose if in this function grad psi, okay, grad psi is a large number. What does that mean? That means when you go from this point to that point, change of psi will be very large. If you go to, if this value is smaller, that means if you go from this point to its next point x plus dx, the change in value should be smaller. That information is already there in the form of this function. I am not doing, so I am not saying that I am treating this index. So the way I treated x, I didn't do any integration or sum over I. For every I got an equation of motion, right? You said that.
Yeah, right.
Okay, so let's see, just say a few steps, then maybe it will be clear to you what I'm going to do. Just see two, three more steps, then maybe we can come back and discuss. So what I am saying is that there is a field psi. This field, this field has a time dependence in it. Obviously, that is the dynamics, and also has a spatial dependence in it. Okay, but that the spatial dependence we treat as if it's different space points means different generalized coordinates. Now, this quantity and these two quantities are how fast these values will change with time at a given point, or how fast these quantities will change with space at a given time. Clear? So if you want to describe the dynamics of the system, you need both of this information. Now, what I am saying is that how do you constructed your action? You constructed your action in this way. You integrate over time. So you say that there is a principle of least action, where when a system evolves from time, classical system evolves from time t1 to time t2, in that time there exists a function which should be minimized for the actual path of evolution, and then we formulate that action in terms of a Lagrangian. And where this going from time t1 to t2, we are integrating it for this. Okay. In the same way, now you formulate a system of fields where the coordinates are this thing. Let's see if you can understand it now. Where the coordinates are this thing. Okay. Now, So you put your action in the same way. So it is, this is into a Lagrangian. This is the whole total L. But this total L now, since X, this position is a, you have an extra extra parameter X in your theory, other than classical mechanics, extra continuous parameter. Earlier you have only I, which is not an, which is a discrete parameter. Now, so therefore we only wrote dt integral L. Okay, qi q dot. All are functions of t. Okay, qi qit. Not only that, it is a function of all these qi's. Okay, earlier we write it that way. In principle, I can also write it in this way here. Say here also I write S as an integral of dt, okay, t2 t1 into an action L, which is a function of the generalized coordinates, which is here psi. Let's write this, draw r comma r for if there are more than one fields, this r comma xt. Okay. Say here psi dot. If I write this way, are you satisfied if I write it this way? If I just write it this way, then it is exactly like classical mechanics, where r, this is the generalized coordinate, this is the velocity. Forget about this. Is it clear?
Yes, okay.
Okay. Now, here it is a function, all this is, these are the coordinates and velocities with all possible r's and all possible x's. Clear?
Right.
So all these x's are there. Now, but since you have all the x's, but x is a continuous parameter, yeah, continuous variable or parameter, whatever you say. Therefore, this thing, that psi dot, this quantity L with all x's, now I can write it in this way. Just this part I write as an integral of d3x, because this L is, to find this L you need a fixed x, fixed t and all the values of x's simultaneously. Clear? But since x is a continuous parameter, you can put it as an integral over all space into a function which is which is this, where x is only one single point here. The effect of taking multiple x's, all possible x's, you are taking in here in this way. Does it make any sense to you? Please look at this equation. Look at this equation.
Sir,
Yes.
so first we are taking all possible x's, then we are taking all possible t.
No. See, this action is a number. Action is not a function. Action is a number. So when you integrate Lagrangian dt, you get the action. It is a number. But at any point of time, so this action is associated with a path. It is not associated with a particular time. It is a path from T1 to T2. To that path, you associate an action and you say that that path is the actual path for which action is minimum. So action is just a pure number associated with a path. Here also. Here also it is, so action is just a number associated with a path of transformation from time T1 to T2. Okay, Now, when you want to write the path of transformation, you have to write dt integral dt into L. Now, your L should be a function of generalized coordinates and velocities. Clear? Your L should be a function of, if I say this and these are the generalized coordinates and velocities only, for with all x's, with all r's and all x, the whole set of infinite numbers. Okay. Now, if that represents the set of generalized coordinates and velocities, then your L should be a function of total L, should be a function of this. So this L is not associated with any particular position point. See, in this case, if I want to write, if I write S by like dtL, where L is a function of only these parameters, this and this, position and velocity, but there are infinite position coordinates, infinite velocity coordinates. Okay, so L, so at any particular point of time, okay, this L has a particular value. This integrated over T1 to T2 gives you S. But when I say at a particular point of time, L has a particular value, but here we are dealing with a field. We have also this space. The space was not there in description of a classical system, because in that space itself, these generalized coordinates are something like that. They are position coordinates. Now your position is a parameter. It's an extra underlying continuum set of parameters. Okay. So what is L? L has a value at a particular time. Now you can't say L has a value as a particular space, because it contains all these coordinates, which are basically the numbers associated with each point in space. Now, it's clear. Suppose you have a material. I give you a material. I ask you to find out the density of that material. What you do? You find the mass divided, total mass divided by its volume. That is the total density of the material. Now, if you wish, you can write, sorry. Just a minute, sorry. Suppose
Hello.
I want to, suppose I, just an analogy I give. Suppose I want to find you the mass of a particle, mass of a system, mass of a large body, large mass of a bulk volume. Okay. So you can write the, you can measure the mass of that bulk volume, but that mass at a particular time. Okay. Suppose at a particular time you find the total mass of the volume, or maybe mass maybe and may not be a, or say, okay. So let's write, suppose at a particular time you find the energy of the system. At a particular time you find the energy of that system. But that system is not a single particle, it is a extended object, it's a bulk system. So it is possible you can write it in this way. Where what is rho? Rho is the energy density of the system. Clear? Where rho has a value at every point in space. Now, when you say the total energy, okay, total energy of the system, to visualize total energy, you have to basically add, you have to consider the energy at all points in space. Okay, but since X is a continuous parameter, you can put it in this form. And all the dynamics of this system, without looking at energy, you can try to look at this. This will capture all the physics which is captured here, because this relations is just a spatial integration. All the physical factor, physical dynamics which is there in rho must be there in E. Or
Yes, I understand that. But in the line you have written A is equal to integral T1, T2, D3, integral all space D cube x, then
yes,
Lagrangian zeta r x, then
no,
mu
okay.
zeta r x. Why you have not written T? Means zeta r bracket x comma T.
Oh,
Why you have
so
not
I dropped it.
written?
I could write T here, but I mean, so I could write T here. Here you say,
Yes, 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 yes.
and it can be an explicit function of T. Okay, but generally we don't discuss the non-conservative system, so I drop T. In for the most general case, T will be here.
Okay.
Sir, here x is continuous, you say,
Yes.
but
This whole thing
x
is the
is,
Lagrangian. This
yes,
entire thing is the total Lagrangian. Is the Lagrangian of the system of fields. This whole thing is a Lagrangian of the system of fields, and this is a function of these two.
yes. But I say that x is function of t.
No, no, no. X is not a function of what x? This x.
X, yes, the argument x.
No, here, here in this case, in this, when I write this, when I write either vector x at t or x, these are the same thing. This x without any vector sign means t and x are there. X is not a function of t. X is just the position. This is not the position of any object or position of any particle. We are this is the value of the field at point x and at point t, at time t. So you say you give as an input t and x, then you get a value associated with that point. That is the value of the field. X is not a function of t.
Yes, sir. Okay.
Now,
Sir, just for clarity,
yes,
when we are in classical mechanics, we know the generalized coordinates, let's say theta, phi, r, etc. in polar coordinate. But when you are dealing with fields, then we know only the functional form of the fields, right?
no, no,
Let's say
no,
f.
no, no, no. You own. So don't think about the functional form. We know the functional form only when you know the behavior of the field. What I am trying to formulate, how to the dynamics of the theory of the dynamics of the field. For that, you have to, because see, when you do Lagrangian formulation, you are arriving at the equation of motion from the action principle. To begin with, you don't assume that you know the function of qt.
Yes, yes, this is right. This is right. I want to say that when we are in classical mechanics, we know the theta, phi, etc. But
We know the
when
theta
we are
phi,
in
we don't know the theta phi, etc. Actually, you
no
identify
means,
the generalized coordinates of a system.
yeah, yeah. I wanted to say that exactly, exactly.
Yeah.
But in case of fields,
Yes.
we identified the field as phi of x, let's say. So, but we need all generalized coordinates. So for that, we need a phi of x plus dx, phi of x plus 2 dx,
Yes.
etc. That
Yes.
that is why we need the special derivative, right? To know the
Yes.
all this.
That's what I am
Okay, okay,
saying.
clear.
That's what I am saying. You know,
Okay, okay.
the special derivative contains in it how at different points, how at different spatial points, the values will be linked at a given time. If you take a different field, it will have a different values. In other
Yes, yes,
words,
clear.
you can take this S, you can take this S, okay, and this Lagrangian you can put it in this way, because this Lagrangian is a function of generalized coordinates, generalized velocities, etc. But you can write as an integral of all space into a function which is a point function. Point function means at every x t and every x, this curly L has some value. Okay, this is not the total Lagrangian. If you integrate it over this, then you have a function L, okay, which is a function of t only because you have done the spatial integration. That thing is this thing. It's a function of t only. These are also functions of time. Okay, because here there is no point of bringing space, but here space is there. But once you integrate it, the space part is, I mean, integrated out. So in the after integration, there is the result of the integration is independent of x. But when you write it in this form, this x will be there. In other words, this action, now I can write, because it is a continuum, the space is continuous, using that, this action with a, earlier we were writing L dt integral, now we can write, just a minute, that may be a problem with my internet. So I have to switch, my internet is gone, it will be soon cut. क्या चल रहा है? हॉटस्पॉट আসছে না তো।
जियो प्राइवेट नेटটা তো হটস্পট দিতেই এর না।
Hello, can you hear me?
Yes, sir.
Sorry. So, so when you are dealing with a continuous system where x comes into your system to serve the role of another index, that because you, which makes the degrees of freedom for the system infinity. Okay, so that allows you to write the action, formulate action in terms of this, where you see your generalized.
Cannot see your.
Hello, can't see your screen.
Okay, just a minute. Sorry. Can you see now? Hello?
Yes,
Yes.
sir.
Okay. Sorry. So this is the, so this Lagrangian, this is called the Lagrangian density of the system. Okay. The thing is that this integration over d3x gives you the total Lagrangian, but the total Lagrangian contains in it infinite number of generalized coordinate to, but you can't handle infinite number of generalized coordinate. To handle that in a more sophisticated way, I mean in a more efficient way, you just put in terms of it in terms of a density, so that it is now a function of this psi and all space derivatives and time derivatives, And now these three parameters, these three things, coordinates, velocities, as well as this space derivative, because these three you have to consider while, because if these three are different, okay, the dynamics of the system will change. Suppose at a given time you have a fixed, these two are same, but this is different. That means the dynamics of the field will be different, because at two different space points, the field variation will be different. The field will be different. Okay, so that goes into the dynamics also. Clear? Therefore, this is the action for the system. Okay. Now, equation of motion means, so let me, sorry. Equation of motion means this Lagrangian density, which is a function of this coordinate and space derivative as well as time derivative. Okay. Because here with velocities, you also need the space derivative of the field. That is not called velocity, but that comes because you are generalized to a system from classical mechanics where the space part plays the change of space is also decides how the change of field with space also decides how the dynamics will be. Therefore, this function Lagrangian density, whose integral over d4x will give you action, is a function of these three parameters, these three coordinate, space derivative and time derivative. And of course, R is the gives you the how many number of different fields you need in your are there in your theory. So delta S is 0 means this here. That means delta of the entire thing is 0. Clear? Is this clear up to this point?
Okay, sir.
So I am applying variational principle, that I say that the whole system of field evolves from time instant t and time instant t1 to t2. When I say it is evolving, I am making no comment out at which point it evolves. I am saying that entire system of field, which in it contains the description of the field at all space points. So I say when the field evolves from t1 to t2, there exists a function L whose integral over all space as well as on all time, that whole integral is extremized for the actual path of evolution. Clear? So it is a generalization from classical to quantum mechanics where, sorry, from classical mechanics to fields, where we need to put this integral extra, because now at every point in space we have the field description. Okay, now if you do I skipped the steps, but you can easily, actually not skip these steps, I have done this, but you can look at it. In the same way we did it for classical mechanics. You bring delta here and find out what differential equation L satisfied. Okay, so that is the Euler-Lagrange equation. Okay, so you delta here, so this means delta of this is 0. So what is delta of this? Delta of this is this. See, now R is a discrete parameter. For electromagnetic field, it is phi and the 3a's, so 4. For other fields, it may be other things. But let's see, if R is a discrete parameter, then this will be a summation over R, because this is the same thing when you do R plays the role of I, more or less. Okay, but you don't take care the role of X here, because you have already, the effect of X you have already put in this integral and brought out a point function in X. So So when you say delta of R, that means you change field by this delta function. What will be the change in this L? So this is this change. Okay. So this is change in phi, and the other thing is this. This contains the derivative of time derivative as well as this space derivative. Here, they are changed. But you don't need to put an integral over x because you have already done this here. Okay, so this was only the difference with the classical mechanics thing. Is it clear to everybody? This Sanjay sir will do it in class, but try to understand it from this point. Then it will be easier for you. So what have I? Is this sentence clear? Actually, here there are four things. Delta time derivative of psi r and the three space derivatives of psi r. Okay, but all I put by this index nu. But when I take this delta of L, I took the derivatives. There is a sum over nu, so all the things are there. This repeated index means sum. Okay, so and there is a sum over R. I dropped the sum here because there is a sum over repeated indices R and mu. Okay. Now we do the same thing. This we put delta, exchange delta here. So bring delta here, and after this step, I can make this. I can write this as a total derivative minus this partial derivative. This is the same thing you do, but you do for classical mechanics. What you do, you just add 3 extra space components here, like this. Earlier it was only 0, delta 0, time derivative. Now there are other space components are also there. So that way we find that this delta L is this, and if we put it back here in this equation, you get this integral d4x into first term and third term together plus this term, which is again a total derivative of something into d4x. Clear? Integral over the entire. So this integral, this omega corresponds to what? Omega corresponds to time wise t1 to t2, space wise all space, from minus infinity space to plus infinity space. Therefore, when you do this integration of the second part, you see that because it is a total derivative, what you will get? What it will get?
0, because in the boundary we consider delta of psi is 0.
Yeah. Okay, in the boundary we call delta of psi equal to 0. Therefore, this term, you will get only this term, which is this equation. Now you can drop this d4x. So this is the equation that L satisfies. Clear? So if you apply variational principle to this, to do this, you have to just identify what are the generalized coordinates of the system. And you see the dynamics of the system will not only governed by generalized coordinates and generalized velocities in this case, but also by space derivatives of the generalized velocities, because space is a continuous parameter here. Clear? You just read this content of this text, which I will send. It will be clear. Because it is difficult to read out these sentences. I mean, without board work, it is difficult to explain more. But this is very straightforward equation, but you have to be very careful about the indices. There are some over indices. You do it yourself. Okay. Now the point is, I know this L. If I know this L, I know the Lagrangian of the system, because if I integrate it over all space, this curly L, if I integrate it over all space, I get the blue thing, which is the total L. So total Lagrangian of such a field I can get, but for fields, total Lagrangian, this Lagrangian density is of more effective than the total Lagrangian because it is a space information, it is a point function of space and time. Okay, because of that, it is enough if you can find L. Okay, that means all the dynamics of this, once you formulate Euler-Lagrange equation for this field psi r, and how many equations are there? There are number of values, possible values r can take that many equations. Here, L will satisfy that many equations. Is it clear? Now,
So R is the number of fields to characterize the system. I mean,
yes,
phi
yes,
1, phi 2.
yes. Like for electromagnetic field, R will be 4.
Yeah. Okay.
Now the point is, okay. So I will. So when I started, so I will go up to 5. So if I have, we know these two equations, these two ordinary wave equations. I want to know, suppose when suppose let us consider Klein-Gordon equation first. This is the equation of motion of the system. In other words, which is equivalent to this equation. So I have to find out what should be the form of L, what should be the form of L, so that if I put L here, it will give you this equation. Clear? That will be the Lagrangian for that Klein-Gordon field. What will be the form of L? If I put it here, it will give us Dirac equation. That will be the form of Lagrangian for Dirac field. Okay. So let's look at the Klein-Gordon Lagrangian first, very briefly. I will do only Klein-Gordon Lagrangian in coming 10 minutes and then stop. For Dirac Lagrangian, I will do it in next class. Okay, let me stop at this point only because I am taking 2 long classes. So this is a good point to stop. For Klein-Gordon and Dirac, I will study, I will teach in the next class. But be careful, be sure that you understand the derivation, do the derivation of this Euler-Lagrange equation and do it your own and try to understand the framework for this. How the classical mechanical system is generalized to map with the system of fields so that I can talk in terms of Lagrangian. Because once I can talk in terms of Lagrangian, all the dynamical properties of the system are encoded in a single function, and that gives me much easier handling of that system. Clear? And try to understand why we have to bring this function in when we generalize. This was not there in a classical mechanical system because there is no underlying space concept there. Space was not playing any role as a parameter in the formulation of classical mechanics. Only time was there, and the generalized coordinates are function of times only. In the far field, fields are functions of time as well as of space. Because of that, this function comes. This dependence you have to take into account. Clear? Any other questions? So I will stop here.
Yes, sir, just a basic question.
Yes.
When we are doing simple particle quantum mechanics for Schrödinger's equation, let's say the wave function is psi as a function of x and t.
Yes.
Again, when we are doing classical field theory, then the phi or psi is a function of x and t. What is the basic difference?
Basic difference is that Schrödinger equation is, so far as xt as parameters are concerned, as you said, their wave function is also function of x and t. Here, wave function is also function of x and t, and there is no difference in that. What is difference in that? In the footing of x and t, because Schrödinger equation is in first order in time, second order in space, whereas Klein-Gordon or Dirac equations are same order of space-time equations. When you quantize
that is okay, but let's say for Dirac equation.
Can you repeat your question? So
Yeah, for Dirac equation, when we are doing single particle relativistic quantum mechanics, then we
Yes.
have psi as a function of x and t.
Yes.
Again, when we are doing Dirac equation as Dirac field, classical field, then this is also psi as a function of x and t.
No, you are talking
So
about the same thing. I don't understand. There are two things. Once you quantize a theory, just you go from classical mechanics to quantum mechanics. Okay, when you suppose a non-relativistic, a classic non-relativistic mechanics, classical mechanics. When you go from classical mechanics to non-relativistic quantum mechanics, what changes happen to your description is that earlier in classical mechanics, the system was described by generalized coordinates. In quantum mechanics, the system is described by a wave function, psi. Okay, you call it a Schrodinger wave function, but that because of that quantization, psi becomes a function of x and t. That is
yes,
that is clear. Now what you are doing? Now you are quantizing the relativistic mechanics. Classical relativistic mechanics you are quantizing. So the effect of quantization is only to describe the function as a wave function, and there you will get a function of x. So this, when you do it, do this relativistic quantum mechanics, you get either Klein-Gordon equation or Dirac equation. Then your wave functions, that phi or psi, they are wave functions satisfying Dirac equation, wave functions satisfying Klein-Gordon equations. You can call them fields, that is okay. But these are just wave functions, just mathematical functions. This is a function of x and t, or Dirac function, which has a 4x1 structure. That is also a form of wave function, or you can call it Dirac field equally. But they are all classical fields. Classical fields means the value of the field is a classical number. So like Schrodinger equation is also a classical field. We just not explicitly say it every time because we call it wave function. By that name it is popular. But a classical field, generally we call a field when the equation is relativist. It has the status of a wave function. Both psi, phi, and the Schrodinger's equation psi, all are relativistic wave functions. All are just classical numbers, either real or complex. Okay, in general complex. The next jump will be quantum fields. Those are different things. We have not come to that point. So for us, we are only talking about classical fields. Classical fields means Dirac field or Klein-Gordon field. They are identical to saying the psi and phi as wave functions. Okay, this so that when we
okay.
say
So
Dirac field, right now we are talking about classical Dirac wave functions or classical Dirac fields. They are just same phrase used for the same thing, different phrases used for the same thing. So effect of quantization is to bring that x parameter in the argument. In classical mechanics, the generalized coordinates are not functions of x because there is no sense of x. A system has some generalized coordinates, they are functions of t. But the moment you quantize, the system is not described by a discrete generalized coordinates. It's described by a wave function, which is a function which has different values at all space-time points at all. Okay, so that functional dependence then came. That comes because of as a result of the quantization. Okay, once you quantize, your field system is not localized. You did a wave function. But the description of the wave function means at every point in time, at every moment of time, you have to know the value of the wave function at all space points. Those are basically an infinite degrees of freedom. A single particle in classical mechanics, a single free particle, which has 3 degrees of freedom in classical mechanics, becomes a system of infinite degrees of freedom when you when you describe it in terms of quantum mechanics. But in quantum mechanics, we generally do not formulate the Lagrangian formulation for just non-relativistic quantum mechanics. We don't do it, but for relativistic quantum mechanics, we have to do it. So for relativistic quantum mechanics, so these things are also applicable to non-relativistic quantum mechanics as well. So that the fact that psi xt can be treated as a generalized coordinate with all x, all values of x corresponds to a particular value of generalized coordinates. In that sense, there are infinite generalized coordinates. But once you formulate this Euler-Lagrange equation, then you take care of taking all possible values of x as the points where you can define it. If every generalized coordinate, that effect can be taken into account within an integration space, spatial integration of a point function of x, so that we can only focus on that point function. Okay, so these are I mean, you have to think. I mean, think about this and then ask. So I request you to, because these are very basic things, I request you to read my class note for my and to come back, and then we will again discuss these issues. Okay.
Yes, okay, sir. Okay, definitely.
Okay. So so far as books are concerned, for this part, what book Sanjay sir has referred to field theory?
What?
Peskin and Schroeder.
Okay, Peskin and Schroeder. You can see why Peskin and Schroeder. These things are there. Why you need x? How you have to tackle this x part in field theory as a generalized coordinate. You can see that. There is also a very good book which I actually I studied in my school college days. I mean, in my university days, and I found it that it is a good book for self-learning. That is a book by Mendel and Shaw. There is a book on quantum field theory by MANDL and SHAW. Mendel and Shaw. That is also a good book. These things you will get very clear picture over there. What I taught in my class. Okay. So, but Sanjay sir will teach this you in detail. But so what we are trying to do, we are trying to formulate an Euler-Lagrange equation for every for Dirac equation, and so we visualize Dirac equation and Klein-Gordon equation as equations of motions of Dirac field and Klein-Gordon field, and we find if is it possible to derive this equation as Euler-Lagrange equation from some Lagrangian. If we formulate it in that way, then the Lagrangian of that from which that equation follows, that Lagrangian will contain in it all the information about the dynamics of the system in the function itself. Then it will be very easy for us to study the different transformations, Lorentz transformations, spin, parity, charge conjugation transformations on the Lagrangian, okay, itself, not on the equation of motion. Lagrangians are always a good entity to study the symmetries of the system. So since we are going to study the charge conjugation, parity, etc., the other symmetries, Lagrangian, we need to know the Lagrangian ultimately. Okay. And therefore the Hamiltonian also. So the entire system, this field theory is formulated by generalizing the classical mechanical Lagrangian formulation. Here, so this is the Lagrangian field theory. So we will only study Lagrangian field theory in the entire MSc course. Okay. So that is the reason. So I am in this class I have shown you how you get the generalization from classical mechanical system to a classical theory of fields by exploiting the Euler-Lagrange technique. Clear? So there are some corrections in this file I am seeing. I will correct it and we will send you this. Okay. Thank you. Okay, bye.
Okay, sir.